Hello, welcome to a video on page 5 of the section 3.2 notes. We're actually not going to do all of page 5, but what we are going to talk about is what is happening with the calculator when you calculate the numerical derivative, and then do examples 5 and 6. We won't get much further past example 6. So let me pull up the calculator here so we can see exactly how to calculate derivative, which we did do in class, but I'm going to do it again anyway. So here's a nice little calculator emulator. It's just like the TI-84, but on my computer. So we talked about that you could go to Math, and then option 8. That's the derivative, numerical derivative feature of the calculator. And what we did in class, we took the numerical derivative of x cubed when x is 5, which we expect something close to 75 because the derivative of x cubed is 3x squared. Plug 5 into that, you get 75. But notice the calculator doesn't say 75 spot on. It says 75.000001. So what's happening here? How come it doesn't say 75 spot on? Oh, by the way, if you hit alpha window, end derivative's also right there. So a couple places where you can find it. So if we go to the notes, what is the calculator doing when it calculates the derivative for you? So it's not actually doing the whole limit business of like, oh, here's, x cubed, let's do f of a plus h minus f of a all over h, limit as h approaches 0. It's not really doing that. It's doing an approximation. So here's our point that we want to find the derivative of. So a comma f of a. Let's say we choose a couple points, one to the left and one to the right of point P. So we have point Q, which has an x coordinate that's 0.001 less than the x coordinate of point P. We have point R, which has an x coordinate that's 0.001 greater than the x coordinate of point P. So what end derivative is doing is taking the slope of the line through R and Q. So it's basically subtracting this with this and divided by the difference of that and that. That's how you get 0.002 on the bottom, and that's what up top we have f of a plus 0.001 minus f of a minus 0.001. So that's called the symmetric difference quotient. I guess it gets the name symmetric because you're picking 2 points that are of the same distance away from P but in opposite directions. Maybe that's why it gets that name. A somewhat better approximation is right below, f of a plus 0.001 minus f of a over 0.001. Where essentially we're substituting 0.001 in for h when we think about f of a plus h minus f of a over h. Now neither is a limit, so it's just approximations. But it does get us pretty close to the actual derivative. So what we're going to do is we're going to try examples 5 and 6. So we're told f of x is 2x cubed minus 9x squared plus 13, and to find a symmetric difference quotient as an approximation. So in other words, we're doing what the calculator does when it finds a numerical derivative. So I'm going to do, so f prime of 7 is going to be approximately f of 7.001 minus f of 6.999 all over 0.002. Now you could actually plug in 7.001 manually into f of x and 6.999 in manually for f of x, but I'm lazy. So what I'm going to do instead is go to y equals, type in the function 2x cubed, and you may want to get your calculator and follow along while I'm doing this, minus 9x squared plus 13. Okay. Now I'm going to graph. Well, actually, I'm not going to graph. I'm going to quit. So now, you might remember we did this a while ago. If you go alpha trace, that's how we can locate y1. If you don't have that feature available, meaning you have the older operating system, if you go to bars y-vars and function, you can select y1 that way as well. So 7.001, oops, minus alpha trace, and doing this on the laptop is a little tricky, so you probably are beating me doing this in the calculator. So that's what the top's going to be, divided by 0.002, and you get 168.0002. So 1, and I forgot how many O's we have. Cool. Now what if I went to alpha window, that's the shortcut for nderiv, x. Now I'm going to put y1 in there, so I don't have to retype the function because I already have a stored under y1. And 7. Oh, you get the same thing. So now we know that this is what the calculator is doing. It's just doing an approximation when it calculates the derivative. We actually could have graphed it too. So the graph kind of looks like that. It's kind of wacky. Now, if I go to second trace and select option 6, which is the derivative operation, and select 7, it won't say 168.0002, but it gets us close enough. So you can also do it using the graph as well. Okay, last one. Use your calculator graph the nderiv of the function f of x equals x cubed if possible identify this graph. So how do you graph a derivative? Well, let's first type in x cubed. Very easy. Then what I'm going to do is I'm going to go to alpha window, nderiv. So I'm going to let the calculator graph the derivative of y1. So if I plug in x, alpha trace, y1. So the calculator is now going to graph y1 first, then graph the derivative of y1. And here's the thing. I don't want it to graph the derivative at a certain point, because actually, if I were to punch in, like, say, 3, for example, or 5, for example, it's going to calculate the derivative at x equals 5, which I know was 75.0001. We did that on the previous page of these notes. If you do it this way, y2 is going to show up as a horizontal line. Think about why it would do that. It's graphing just a constant because it's calculating the derivative of y at x equals 5, and that's it. We want to actually get the true graph of the derivative of x cubed, which we know is 3x squared. So what you need to do is you actually need to type it in like that. d dx y1 x equals x. Okay, now let's graph it. There's x cubed. And it's going to take a while because the calculator is actually calculating every single derivative in this window. And see how it graphs it like a parabola, which makes sense. So again, in the calculator, I first do y1 equals x cubed. Then I do y2 is that, y1, and you want to put an x there. And the graph looks like this. And of course our derivative, I'll change colors. Looks like that. And that's pretty much it. So there'll be some homework on just using the calculator when doing derivatives. And that is it. All right, have a great day.